Similar studies done in Canada. This is a species richness across Canada, done from records going back over the 20th century, and then projections using climate change models of how those species will move. And that's the difference there in just a space of about 20 years, a 200 to 300 kilometer range shift. And again, that's all with suitable habitat being available and ability to migrate and so on. We can do this using all of those data points which I showed you that are available through GBIF for plant species as a whole across the globe. Current species richness run against all the climate models there. You see up to sort of 5,000 species per grid square. And when you show that there can't be any migration, you get dramatic species losses. With unlimited migration, you get displacement, but of course there can't be unlimited displacement. So here with no migration, you just see in the key on the left that you just get categories of species loss and depauperization of ecosystems. With migration, you would then get that displacement, so you would get species movements happening. If we look at this, for example, for things like tropical forests, which are really, really important under the Climate Change Convention, REDD Plus in terms of paying for carbon sequestration. This is just 3 tropical forest families, Sticuliaceae, Meliaceae, Dipterocarparaceae. We run the climate change models. We see a loss of species richness there. There's your species richness change, and you can see there's quite a dramatic loss of species richness in those tropical forests. The figures are even more dramatic. Average habitat loss over 50% in all families, percent of species loss more than 50%. The implications for that is that now what do you do when you pay for REDD Plus? Do you pay communities to maintain tropical forests where they currently are and the climate envelope sits? Or do you pay for where the climate envelope may move into the future? And at what point in the future are we going to be able to track where that goes? And how do you ensure that those species move? So there are a lot of implications around what's happening with biodiversity for a lot of the adaptation or supposed adaptation models that we have on the table under the Climate Change Convention. The same with the major vertebrate groups, amphibians, reptiles, birds, mammals. These are potential refugia under a 2-degree sea rise and run against, again, the global climate models. So these are the areas where climate envelopes will remain fairly amenable to the species that have co-evolved with them. But of course, if the temperature goes up, you'll see those refugia all contract. Now, if you're going to try and put in representative protected areas, for example, like the new target under the Convention on Biodiversity, you need to put them where you're going to be protecting rare endangered species or which are representative of biodiversity. There's no point putting them in areas of mass extinctions. So if we just flip those models around, so where are the climate impacts going to be the greatest? Where are you going to lose the greatest complement of species? And at 2 degrees sea rise, these are the areas which show that there'll be mass extinctions under those climate models. And as that temperature goes up, so those mass extinction extents expand hugely. In South Africa, we've done a lot of intensive work around this. There's a dramatic change in the ecosystems that make up South Africa, the biomes. The top left is the current existing main 9 biomes, and the bottom right is what will be remaining of those by 2050 under the sort of climate change scenarios. What's really, really scary about that map is that the white areas in the bottom graph are biomes that don't exist in South Africa today. They're desert. And if we look at that just in the Cape Floral Kingdom, the only floral kingdom of 6 around the world, which is contained within one country, it's where the wine-growing region of South Africa. The red area is what the total expanse of color there is the total biome. The red area is what would be lost by 2050. The green is what would persist, and blue would be where there would be an expansion, and that's really up to the top of the mountains that occur in the Cape. However, if you look at individual species, whether they'll be able to respond to that, the red area there is the extent of the range of this protea species, with the green dot in the middle of the red, its current center of its range. And then those green dots moving down are 10-year time slices, how that species would move with climate change. And the blue is where by 2050 would be suitable habitat. As you can see, there's virtually nothing that's available. But also in between is the city of Cape Town and the Cape Flats, and totally covered with habitation and so on. So even if the species could physically migrate, it probably won't be able to. What does this mean for impact assessment? It really means complete change in approach in terms of the time span of the impacts that we normally assess. We're having whole biome shifts, species total range shifts, and these cannot be measured on individual projects. Cumulative impact assessment is absolutely imperative as we go forward, strategic assessment, and restorations of previous degradation become an absolute requirement of every project now in order to facilitate the restoration of those ecosystems. So connectivity is absolutely key going forward under impact assessment. Most species are just going to have to fend for themselves. There's no ways that we can try and manage conservation for all of the biota that are out there. We don't know which ones are going to be winners, which ones are going to be losers under climate change. So we have to try and build the connectivity and the contiguity between habitats. So every activity that is assessed would need to be assessed for its ability to build and restore connectivity and functionality in ecosystems. I just want to talk about invasive species quickly. By having these data sets, we're able to track where invasive species will be and create ecological niches from the historical record. So this is a disease-carrying mosquito, the native range in Asia. That ecological niche model was transposed onto the continental United States, and then these are where the mosquito has been observed already in the United States by county. So that has huge implications for your medical and health services and where to put your responses. That's just the global map. I'll go through that quickly. But the big question about invasive species is to say, at what point in time is a species alien? Okay? Climate change is truncating these geological time spaces. So biodiversity is on the move at unprecedented scales. We're going to have to recategorize invasive species into basically not invasive, but being harmful, benign, and beneficial. So some disease vectors, like the mosquito I just showed you, we want to combat. We want to prevent its extension. But things like pollinators, if we're going to lose all our pollinators wherever we are, and they're going to shift with range changes like I showed you, you want to encourage other pollinators to come in and replace that. Categorizing those as invasive alien species, because they didn't occur in your country previously, is just nonsensical. So we're going to have to really adapt with climate change to the way we think about, or we previously thought about biodiversity. I'll just skip that picture quickly. I think a lot of people have seen it. But if we want to prevent this type of thing, we have to put things in place. And one of the best ways to do that is ecosystem-based adaptation. It includes a range of local and land-scale strategies for managing this resilience of ecosystems by incorporating biodiversity. It removes the canalization, for example, of rivers and puts the floodplains and the bends back in the rivers to work in preventing floods. Rehabilitation of mangroves, everybody's heard about, and so on, building artificial reefs, which I'll show you in a minute, which then become living breakwaters, because if you put an artificial structure down, it becomes populated by biota, and it becomes much, much more effective as a breakwater. As soon as you plant up natural biota, you plant up mangroves, and you manage them, they start to regenerate themselves. So these living biodiversity buffers are the best way to adapt to climate change. And there are all sorts of ways of integrating those with hard infrastructure as well, and that's also an opportunity, which is we mix and match sort of hard engineering with soft engineering approaches. So just getting back to that original diagram, the implications for impact assessment are that we have to make sure that when we do assessment, it's pushing us back into those ecological boundaries which we have to maintain, where we've exceeded them already. And that's critical to understand whether assessments are being done correctly or not. So increasingly, restoration of all of these major ecosystems will be needed to reestablish ecosystem functioning. That's from the report Dead Planet, Living Planet from UNEP. It means that every impact assessment must contribute to restoration of existing deficits and not just look at what impacts will result out of that. And every impact assessment must contribute to mitigation and adaptation. So new approaches for impact assessment then, just to wrap up, we have to respond to this evidence that current trends are not viable. Impact assessment must evolve to lead recovery of that planetary deficit, which we've seen already. The world is we can't manage for stasis as we have previously. The world is in an increasingly rapid flux. It's going into exponential flux. Ecosystem-based adaptation, which is built for change. It's built to absorb change. It's built to work with change. We must work with connectivity and not work within bounded areas. So we must work with cumulative impacts, strategic assessments, and so on. And ecosystem-based adaptation is really the single most cost-effective long-term adaptation strategy for climate change that we can use. Thanks very much.